Hey guys, welcome back to this discussion about working with imbalanced data. I say welcome back because in the previous tutorial we talked about imbalanced data or 7 techniques to handling imbalanced data by using a image segmentation as an example, where one of the regions was underrepresented and a couple regions overrepresented. And we realized that upsampling is an effective way to handle imbalanced data. That doesn't mean it's the answer for every type of challenge. So in this tutorial, let's look at a different type of data set. This is obviously a non-image data set I'm going to talking about, and this is liver patient records from India. So in this data set, by the way, you can actually get this data set by just Google searching for liver patient records data set. And it's part of kaggle.com, and I'll leave the link down in the description. Now, just to quickly understand what the dataset contains at a very high level, the dataset contains 416 patient records, meaning they have liver disease, and 167 non-patient records, meaning they do not have this disease. Of those, all of these combined, 441 are male and 142 are female. As you can see, the non-liver patients are undersampled, and even the females are undersampled. So there are many opportunities for us to handle this imbalanced data. For now, in this for this tutorial, let's actually focus on enhancing this or embellishing or improving this 167 in a way that our overall accuracy improves. Okay, so for that I'm going to do upsampling. Let's go ahead and check that out, and also SMOTE, where we are synthetically generate minority data to make sure we're not imbalanced anymore. Okay, again, that may not be the right approach, but we'll find out. Now, just a quick run through this this data set. It's got a few of these features, if you want to call them features, but you have the age of the patient, gender, total bilirubin, and a bunch of other measurements taken, including albumin, and globulin ratio. Okay, if you don't know what that is, it doesn't matter. These are a bunch of numbers for us. And finally, the last column labeled as dataset. This actually has a value of either 1 or 2. Okay, the value of 1 means yes, it's a liver disease. Value of 2 means no, not a liver disease. Okay, so this is something that we need to keep in mind. Now let's jump into Spider. As usual, I'll share the code with you, so please do not write down or try to code while you're watching this video. I believe that your time is well spent just by watching, focusing, okay, and then do things later on. Okay, I added, basically copied and pasted this, added a bunch of text up here. And by the way, you can find my GitHub. Again, the link is down in the description. So go ahead and download the code. So let's start by importing the Excel file. So this data set is in the form of an Excel, and all of these libraries are standard, right? NumPy, OpenCV, Pandas, Matplotlib, and Seaborn for plotting. So let's go ahead and import those lines, and then let's go ahead and read the data frame. So let's read the data frame, and it shows up in my variable explorer. As you can see, it's got 11 columns. 10 for features and 1 as our label. So if I open this, let's have a quick look at it. Let me expand this so you can see it a bit better. So here, the first column is age, gender, and then comes these other measurements, okay? Total bilirubin and all of these other. And the last one, data set, either 1 or 2. Again, as I mentioned, 1 represents yes, it's a disease. 2 is no, it's not a disease, okay? This patient does not have a disease. And also one thing you'll notice is some of these values go between around 0.1 to 0.2, 0.3, and this one is 60s, 70s, 80s, 90s, and this one is, again, so the range is different. Oh, we need to handle this, not a number. Looks like there is some missing values for this last but 1 column. Again, we'll go through this in a methodical way, okay? I just don't want to make this a imbalanced data video. Whenever I do my videos, I want to make sure I go through the code so any gaps in knowledge can be filled easily, okay? So this is a quick overview, but we'll get much better understanding. First of all, let's look at the DataFrame.describe. Okay, so when you do that, it actually gives you all the information. Let me create a bit more room here so you can see everything clearly. Okay, so the age, we have total 583 records. Of those, the mean age is 44.7. and you can see minimum, max, and all that information down here. Okay, and again, like I mentioned earlier, see the mean value here, 290, 80, 109.9, but then all of a sudden you have 0.94 and 3.29. Most of the time, it depends on the algorithm that you pick, the approach, whether it is linear regression or random forest or support vector machines or deep learning, but it does make sense to normalize these values. Otherwise, depending on the approach that you picked, your model may be biased towards larger values. Okay, so normalizing is one of the steps we need to do. Okay, so first of all, and we think, I mean, at least we caught one null data set. So let's go ahead and see how many null data sets, data points we have. And again, I covered this in our pandas tutorial, right? So your DataFrame.is null and sum all of those. So it prints out a summary like this and looks like albumin and globulin ratio. We have 4 missing entries. We can drop those 4, but we barely have enough data points. So instead of dropping it, let's fill those with average value, which is, I think, okay. It's up to you. You can drop it if you want. So for that, let's go ahead and find out what the mean value is. Mean is 0.947. That's exactly what I'm filling the missing values with. Okay, so let's run these 2 lines, and then at the end of it, we should see that, okay, we have no null data points anymore. Again, pre-processing takes, I think, 90+% of your time, and the actual training part is pretty straightforward. Now, let's, for one thing I don't like is the label dataset. It doesn't tell you exactly what it's doing. So let's change the column name to label. This is, again, it's up to you. You can change that to, is it a patient, or, it's up to you. Okay. Now let's understand the data. First of all, let's actually count plot. Okay, again, I like Seaborn. You can do this in Matplotlib, or even just use df.plot, like, use pandas built-in plotting, which uses Matplotlib anyway in the backend. Okay, so my plots are in a separate window, so you can see. Like the documentation says, I have 400 some positives or patients, and then about 150 or so. Let's go back and see how many. 416 of this and 167 of non-patients, right? So again, I'm trying to understand the data so I can better define my approach later on. Now let's see how it breaks down into gender. Again, we have a lot more male information, but then we have, as you can see, more data with label 1 corresponding compared to label 2. And let's look at age. I mean, is there any, again, how does the age actually, is the age skewed towards older or younger? No, it looks like about 40 to 45 years is where, it's peaking, but we have information, unfortunately, for patients as young as a few years old to 80 plus, like almost 90 over there. Okay, so this is a nice looking like a normal distribution over there. And what else? Age. Let's actually look at how many patients of a certain age group. Like, is there a specific age group that are susceptible to this disease, or not susceptible, but is represented in our data set more than others? So apparently, age 60, we have like almost 34 people with age 60 represented, with or without disease, that we don't know, but chances are most of them are with disease given how our data set is spread. Then comes age 45, 50, 42. So it's not like there is a trend. It's not like, okay, 60 and 55 and 50 and 45 and 40. So it looks like it's relatively random, because I see 74 here, 68 here. So at least right away it tells me that, okay, maybe for whatever reason 60 years is represented more, but I don't see a big trend. Okay, let's look at the albumin information. Again, for label 1, this albumin is going all the way from value 1 to value 5, 6. Again, I'm looking for any clusters. Like, for example, is there a cluster towards high end in albumin for label 1 versus label 2? No, they both seem to go pretty much 1 through 5. So I don't know if, so looks like this is not at least correlated with albumin levels. How about albumin to globulin ratio? Usually it's not, these type of challenges are not that simple, right? It's not just one that tells you, oh yeah, this is a indicator of liver disease or something, right? So it's a combination of different things, and that's why we need something as sophisticated as support vector machines or random forest. Okay, so let's do one more thing. How is albumin and albumin to globulin ratio? I don't know what information that gives, but you can just go ahead and plot and see if that makes any sense. I did comment out this pair plot, but sometimes pair plots can actually give you very nice information. It takes a bit of time on my system, so I'm not doing that. Instead, let's actually look at the correlation, like almost like our matrix. You'll see that in a second. There you go. And this kind of gives you an idea whether something is correlated. And let's look at the label column right here, right? I mean, to the label, albumin to globulin ratio is positive 0.16. Maybe this total protein is not a strong indicator because the value is 0.035, but everything else is around 0.1, 0.1, 0.1. To me, it sounds like they all have equal weight, or they are all probably going to show almost equal weight. Because we have 10 of these, maybe each of these will have a weight of 0.1, yeah, in defining whether someone has the disease or not. Again, this is just my hunch. Let's go ahead and see how that works out. And finally, let's look at the gender value counts. Like it said, we have 441 male and 142 female, right? So these guys did a good job in describing the data set, so we don't have to do this exercise. But typically, this is what we do when we get a new data set. Okay, now what I'm trying to do is, if you look at this data, when I'm trying to fit this, fit this to a model, everything is a number except for this gender. Gender is female and male, right? So I cannot work with female and male here. And also, it looks like there isn't much of a strong dependency on whether it's female or male when we plot it. So we may as well drop it. But if you don't want to drop it but include that as part of your training, then you have to reassign these values. So what I'm doing is basically replacing the categorical values with numbers here. Okay, so my male, I'm going to replace male with 1 and female with 2. That's pretty much what I'm doing here. So let's go ahead and finish that point off. And again, if I open this, instead of male, female, you should see 1 and 2. Okay. Now we are almost getting there. So our Y, which is our labels, right? So what is our Y? The Y value that we are trying to predict is our label values. So from the data frame, get the label. Now, what's our X? Our X is everything. Let's go ahead and drop label and gender. Well, we reassign gender, but let's go ahead and drop it. Okay, so when we do that, our X should actually have 9 columns. So we have 9 values that we're trying to fit. Now, I did mention about these values, again, going back, ranging from, 0.7 to 10 to 100 to 699 for something. So we don't want our model to be biased towards larger values. So let's go ahead and normalize them. And there are many ways to normalize it. You can find the average, you can find the maximum and divide them, but I like to use keras.utilities, normalize, and also even in scikit-learn there is a normalize, so go ahead and use whatever you think works. This one works pretty nicely. I believe when we say normalize, it's not just dividing it by the maximum value or something, but it's also centering all the data set towards the mean. So again, it's been a while since I looked at this documentation, but please go ahead and look at the anytime you apply any function, obviously you're going to look at normalize, its definition. So okay, my system is taking a little bit in doing this task because it's trying to import TensorFlow, which is the backend of Keras anyway. Okay, so now our values are normalized. If I open my X, you should see that all the values are 0.00 something, 0.9. So all the values range between, apparently in this case, 0 to 1. Okay, now we are all set. Well, one final step before moving on, just like we normally do, split the data set into training and testing, so we can testing it on the held out data. In this case, we are holding out 20% of the data set. Okay, now comes the training part. Again, just like in the previous tutorial, I'm going to give you the code by commenting out the logistic regression part and also support vector machines. But you go ahead and test this out, which model works best for your data. Okay. For now, let's focus on random forest classifier because I'm a big fan of random forest classifier. Usually it works very well on imbalanced data sets. Okay. That was our technique number 1 from our previous tutorial in handling imbalanced data. And I'm going to use 25 estimators. Again, if you use a lot more estimators, then it gets super overfitting to the training data. It doesn't work very well on the testing data. Okay, so estimators anywhere from 10 to 50 experiment. Given that I have 9 columns, 9 features, maybe 50 is too much. Okay, so let's try with 25 estimators. Okay, and again, if you don't know what I'm talking about, look up the documentation for random forest classifier. In fact, look up the original paper. I think it's by Bremen, whose tomb is very close to my house. It's in Berkeley, but Bremen is the guy who came out with random forest. Anyway, so let's go ahead and fit a well, first define the random forest, okay, and then let's go ahead and fit it on the training data set. This should be pretty fast compared to our last run in the previous tutorial. There you go, that's done. One thing that's great about random forest is it tells you which features actually helped in defining the model better. Okay, so what in a way it lists out or it reports the feature importances. That's why I like this very much. So let's see which features actually have weight. And well, as I guessed earlier, almost every feature has a weight of 0.1, 0.1, 0.1, because we didn't see a clear trend anyhow. So it looks like they're all contributing towards this model equally well, except for these two. These are all pretty close to 1 anyway. So to me, they're all pretty much equally distributed. Okay. Now let's get back to predicting the values. Let's go ahead and predict it on the X test. Once we predict, let's go ahead and print the accuracy. Again, I covered this many times in the previous tutorial, so I'm not going to talk about it. So our accuracy is 72.6%. Again, accuracy is not a great metric because the majority class may do great and the minority class will not do great. And when you do accuracy, the minority is not well represented. So first of all, let's go ahead and look at the prediction unique. So the value of 1, 93 data points, value of 2, 24 data points in our testing data set. So value of 1 is overrepresented. We know that anyhow. Okay. So now let's print out confusion matrix. Okay. Again, we did pretty much the same thing in our last tutorial. So as you can see, 74 labeled as 1, correctly identified as 1. 19 of the total 93 are mislabeled as 2. Okay. Exactly opposite. This is actually doing pretty bad. As you can see, the 11 here represents the healthy or non-disease individuals, and 11 out of 24 are correctly labeled and 13 out of 24 are mislabeled. So our model is doing horribly, very horrible on these healthy patients. So we are actually calling a bunch of these healthy patients, or healthy individuals patients, or, with disease, which is also not acceptable, right? I mean, in this case, we need to get, let's see how to improve the accuracy. Okay, so let's actually first of all print out the individual accuracy values. So for that, I'm just using confusion matrix to print this out. And with lung disease, 79%, no disease, 45.8% accuracy. We just saw that, right? I mean, it's not doing good on this. So our goal is to improve this as much as we can. And the other metric that's actually useful for especially these type of binary problems is ROCAUC score. Okay, so you can go ahead and print out the score here, but more importantly, it's good to actually plot it out. And one good way, I think in scikit-learn, you can use ROCAUC, but I recently discovered this Yellowbrick classifier. Again, here is the documentation. Just go ahead and Google search for Yellowbrick ROCAUC, or I'll include the link anyhow. And this makes it very easy to plot. Okay, you'll see that in a second. So I'm importing ROCAUC, and I'm applying that onto our model, which is what we call model underscore RF, and then we are fitting it and score and show. Okay, all of these at one go. So we should be seeing a plot all I'm doing is exactly following what these guys actually defined here. Instead of visualizer, I just called it ROCAUC. That's pretty much it. Okay, let's look at the plot. Let's go ahead and plot this one more time. There you go. Okay, so there you go. That's the plot. Now, again, please watch my video about ROC. If this is a good classifier, then the model would go to the top left and then to the right, right? It's almost like following these axes up there. This is okay. This is not good, but this is okay. Let's see if that can be made better, again, by handling our imbalanced data. Now, the real reason why you're probably watching this video, how do I handle imbalanced data after, I guess, 18, 19, 20 minutes into the video? Now we are getting to this. Let me go a bit fast now. Okay, so what is our technique to improve or to upsample our minority class? How do we do that? Again, these are pretty straightforward. Let's go ahead and oh, by the way, I should have explained this. We are going to use resample from scikit-learn utilities. Okay, and then I'm printing out the labels. Again, we have 416 of label 1, 167 of label 2. So I'm separating our majority and minority. Okay, everything that has a label of 1, I'm calling it majority. Everything that's a label of 2, I'm calling it minority. Now, I'm going to apply my resample method to my minority data set only. Okay, so to only this data set, and replace equals to true, and number of samples 414. Because we have 416 there, we may as well change this to 416. Okay, number of samples. And random state is just a seed that it's using to generate these numbers. So it's going to randomly pick data points and then replicate them. Again, it does it in an iterative way. Randomly pick data points and copy them. That's how this thing actually works. So let's go ahead and run these lines. And it's done. Now let's go ahead and combine our majority and the upsampled. Okay, so all I'm doing is separated majority and minority and upscaled minority and combining majority and the upscaled versions. That's pretty much it. So I'm doing that right here, concatenating both data frames. And finally, let's actually see, count the values again. So now I have 416 for label 2, 416 for label 1. So there you go. This is how we upsample. Now let's do pretty much the same as what we have done before. Define our Y as the labels and define our X as all the columns except for label and gender. Let's go ahead and run that line. And normalization, right? So do not forget to normalize the values. In fact, it'd be nice to actually not normalize and see how this ROCAUC looks like, or your confusion matrix looks like, and then do normalize and see if it has an effect. Very good learning opportunities, you know. Okay, now we're going to split the data just like before. I'm going to train our random forest. Again, nothing new here. Train upsample not defined. Oh, I didn't run these lines. Let's go ahead and run all of these lines at the same time so we don't forget. Now let's start reporting our metric. Okay, so first of all, let's do our accuracy. The overall accuracy went up to 86.2%. If you remember, the overall accuracy previously was, if I can find it, 60. Oh, sorry, that's ROCAUC. The overall accuracy was 72.6%. Okay, so now we went up to 80. I guess it helped. And also previously we had 79.5 and 45.8 for individual class accuracies. Now let's actually go ahead and print those, and we should see better. 92.4 and 80.6. Much better than before, because now no lung disease is a bit well represented compared to before. Of course, nothing beats collecting more data, but if it's not an option, then these are the tricks you can do. Okay, so let's go ahead and plot our ROCAUC. Hopefully it should look slightly better than what you have here. There you go, and much better, right? So this is the one we had from before, and this is what we have now. So much better model, because again, you may want to plot this using support vector machines and also the other techniques. Okay, so I'm just sticking with random forest for now. Now, so that's our upsampling, and upsampling is working great, and I recommend doing that before you do anything else. The other option would be that's potentially worthy looking at is SMOTE, right? Synthetic minority oversampling technique. It's synthetic because it takes a couple of data points, and I think it averages all the values and then creates a new data point. And there are methods how it generates synthetically these data sets, and I'm including this link as part of the code. Go ahead and check it out and learn more about this. Okay, so instead of going line by line, now you know the drill. All I'm doing is importing SMOTE from imblearn. Go ahead and pip install imblearn and imports SMOTE, I guess you can call it. And then you fit it, and everything else is just like we did before. So this step actually generates your X and Y, upscaled data. And let's go ahead and run everything at the same time so we can have a quick look at the final. First of all, you see it generated 416 and 416 data points. Okay, so it balanced it, and here is how the output looks like. Okay, let's summarize this. So without doing anything, imbalanced data set looks like that, ROCAUC. SMOTE looks like this, somewhat better, still not as better as upscaling your data. Okay, so this is how, again, on a data set that I literally Google searched to find an imbalanced data set, and this one I think is a good data set to learn traditional machine learning in general. Now I leave it to you to actually now fit a quick deep learning model, whether it is like a couple of dense layers, or you want to get a bit more fancy and include more dense layers. It's up to you, but I think with deep learning you can probably get do a bit more experimentation with upscaling and also by other means. Please watch my previous tutorial if you don't know what I'm talking about. Anyway, thank you very much for your patience. Again, one of those slightly longer videos, but I hope you find this time to be well spent. So in the next tutorial, let's learn something new. Thank you very much.